There is an important intuition behind LSH and similar concepts called dimensionality reduction. Now, think of the space or the collection of objects. For example, you can think of fingerprints. It's d-dimensional, where d is 1,000, because every print can be represented by a d-dimensional vector which has ones and zeros, ones where there are minutiae and zeros where there are not. 1,000 because we had a 25 by 40 grid. There are lots and lots of possible objects in this space, not all of which are fingerprints, but definitely the space is very, very large. 2 to the 1,000 is really, really huge. What LSH does intuitively is it reduces the dimension to just B hash values, and B is small, 1024 in this case. Further, the fact that we use random hash functions turns out to make them locality sensitive. Now, this is a very deep idea that random choices and random functions actually work really well, and we won't delve into why that happens right now, but that's another important intuition. As a result, similar objects map to similar hash values. It also turns out that LSH techniques are closely related to other kinds of dimensionality reduction methods, such as for discovering topics in large document collections, objects in videos and images, and many other. A caveat though, implementing LSH can be a bit tricky, especially in parallel. That's something we're going to look into during our discussion on big data technology and MapReduce. Let's return now to our hidden agenda about trying to understand something about human memory from all the techniques that we have been studying. One question we should think about is, do we actually store all the objects, such as images and experiences, that we get exposed to? Do we have a large disk space somewhere in our head where things are just kept in full fidelity? Probably not. Way back in the late 80s and early 90s, Pentti Kanerva, then working at NASA, came up with a concept called sparse distributed memory, which tried to model how humans actually store data, in particular high dimensional data like images, experiences, and many of the things that we are exposed to are high dimensional. So this stuff predates LSH, is also related to high dimensional spaces, but rather than reducing the dimension, it also exploits the fact that the space is high dimensional. Sparse distributed memory exploits some rather peculiar features of high dimensional spaces. An example of a high dimensional space that we've already seen is the space of 1,000-bit vectors, such as all possible grid cells of 25 by 40 with ones and zeros that we use for fingerprints. There are lots of these, 2 to the 1,000, many, many hundreds of zeros behind that. Now, think about any two random 1,000-bit vectors. What would be the average distance between these in terms of the number of bits in which they might differ? What do you think? Well, it's quite obviously 500, because on the average you would toss a coin to decide whether the two vectors differed from each other, and half the time they would and half the time they wouldn't. So in half the bits they would differ, in half they would be the same. Now consider a vector x chosen at random. Could be anyone. We start from this one vector x and ask us a few interesting questions. Clearly, half all of the other vectors are less than 500 bits away from this vector, and half of them are more than 500 bits away from this vector. That is, again, obvious by choice, by tossing a coin. The really interesting thing is when we ask the question, how many of all the other vectors differ from our chosen x by less than 450 bits. Now remember, half of the vectors differed by less than 500 bits. But how many differ by less than 450 bits? So if we toss a coin, and if the coin comes up heads, we assume the other vector differs from x, and otherwise it doesn't. So we toss 1,000 coins and figure out what's the chance that we'll have less than 450 heads. Actually, it's quite a small chance. That comes from probability theory. We use the binomial distribution with a mean of 500 and n equal to 1,000 because we're tossing 1,000 fair coins. The standard deviation of this is square root of 250. You can look this up in any probability textbook. We approximate the binomial distribution by a normal distribution, and then we see that, very interestingly, a very, very small fraction of all the other vectors are less than 450 bits from x. So what that means is that with a very, very high probability, most of the other vectors are within a band of 450 and 550 bits away. Remember, the normal distribution is symmetric, so what we did for how many other vectors differ from x by less than 450 can be repeated symmetrically for asking the question how many will differ from x by more than 550. So we have this very interesting situation that almost all vectors in this huge space are far away from x, somewhere around 500 bits away.